For years, we've kind of thought of AI as this disembodied brain, right? A powerful intelligence just living inside computers. Well, that is changing, and it's changing fast. In this explainer, we're going to look at how AI is not just getting smarter, it's now getting a body. It's developing superhuman physical skills, and it's creating a whole new ecosystem that's actually starting to improve itself. Okay, let's dive right in.
So the moment that really signaled this massive shift didn't happen in some data center. Nope. It happened on a table tennis court. Sony AI's Project Ace, which is this autonomous robot, did something that a lot of people thought was pretty much impossible. It went head-to-head with professional human players in a real-world, high-stakes match, and it won. And look, as the project's own chief scientist, Peter Stone, pointed out, this isn't just some sports story. This achievement is a landmark. It's proof that AI can finally operate in the messy, chaotic, super high-speed physical world at a level that can match or even beat human experts.
So, what does it actually take for an AI to make that jump? To go from the clean, predictable digital world of, say, a chess game to our messy, unpredictable physical one? Let's break that down.
For decades, this so-called reality gap was the biggest hurdle in robotics. See, an AI could master a game with a clear set of rules, no problem. But the real world, with all its crazy, chaotic variables, that was a whole different story. Project Ace didn't just close that gap, it basically leaped right over it. I mean, just imagine trying to process the spin and the velocity of a pro's shot, and then reacting with superhuman precision, all in less than a millisecond. It's wild.
But a feat like this doesn't just happen in a vacuum. It takes a massive technological foundation. So let's look at the infrastructure, the skeleton and the nerves, if you will, that makes this new kind of physical intelligence even possible.
The key term to know here is agentic AI. And we're not talking about simple chatbots anymore. Agentic AIs are autonomous systems. They're designed to handle complex, multi-step tasks all by themselves. They perceive what's around them, they make a plan, and then they actually act on it. And this new era of agentic AI needs a completely new kind of engine. It's not just about the software anymore. We're talking about an entire technology stack built from the ground up, starting with incredibly dense foundational silicon, then moving to specialized chips designed specifically for AI, all the way up to the agent software that can finally make sense of it all.
At the very foundation of this, the level of miniaturization is it's mind-boggling. We're talking about 1.6 nanometer technology. To give you some perspective, this is the kind of breakthrough that lets us cram the power of a giant data center into smaller, way more efficient devices, the kind of tech that can actually live inside a robot or a drone.
Then, sitting on top of that silicon, you have these specialized chips, like Google's newest TPUs, and they use a really clever approach. One super powerful chip does the heavy lifting of training the AI, and another, much more efficient chip, handles the inference, that's the quick real-time thinking a robot needs to act. This is absolutely key to lowering the massive operational cost, what they call the inference tax, that has always made powerful AI so expensive to run. Okay, so we have the body and we have the nerves. Now let's look at the brain, the AI agents themselves. And this right here brilliantly illustrates the double-edged sword of creating such powerful autonomous tools.
And this is where we really see the two faces of agentic AI. On one hand, you have an agent built to be the perfect research assistant, pushing science forward. And on the other hand, you have a red teamer, one that's designed to think like a hacker and break things, except it does it with terrifying efficiency.
ML Intern is a fascinating example of AI improving AI. It's an open-source agent that can basically conduct its own machine learning research. It finds papers, generates data, trains new models, and it's even outperforming established benchmarks. The acceleration is really starting to feed on itself.
But then there's the flip side. A massive model called Claude Mythos 5 was found to be terrifyingly good at finding zero-day vulnerabilities. Now, these are brand new, unknown security flaws that nobody has a defense for yet. Its abilities were so powerful that its own creators at Anthropic decided it was just too dangerous to ever release to the public. So this brings us to a really fundamental question, doesn't it? When we create agents that can act this independently and this powerfully, how do we, or can we even, make sure they're only used for good?
Which logically leads us to our final section, the frantic global race to govern this new reality and to somehow set the rules of the road for AI. The conversation has just completely changed. It's not a technical question of how powerful can this get anymore. It's a geopolitical one of control. Governments now see unmanaged AI not just as a risk, but as a potential threat to their national security and economic sovereignty. So all of a sudden, every major power is asking this same exact question. How do we control this without falling behind? And the pace of government action is accelerating dramatically. I mean, we saw a presidential directive in late 2025 calling for a national AI framework. Then, just a few months later, in April 2026, we saw bipartisan legislation moving forward to restrict the export of the very semiconductor tech that powers this whole revolution.
And the result is this constant tension. On one side, you've got companies racing to commercialize these incredible new tools. And on the other, you have governments trying to pump the brakes, putting in national security controls to try and manage the risks. It's a real tug of war.
So, what does all of this, the robots, the chips, the agents, the politics, what does it all add up to? Well, we're no longer just building individual tools. What we're witnessing is the birth of a closed-loop AI ecosystem. And this right here is probably the most important takeaway. It's a cycle. Specialized hardware enables powerful autonomous agents. Then, those agents, like ML Intern, turn around and accelerate the design of even better hardware. And that better hardware, well, it powers even more capable physical robots, like Project ACE. Each part of the system is now making every other part better, faster. It's a self-reinforcing, self-accelerating loop.
Which leaves us with one final and pretty crucial question. As this entire ecosystem becomes more autonomous and more self-improving, what does that truly mean for our future? For the nature of work, for the pace of innovation, and ultimately for the role of human control.